Okay, let's continue our conversation about conformational analysis, and we're going to switch now to discuss cyclohexanes. I mentioned in a previous lecture that cyclohexanes are quite common in organic chemistry. And it turns out that they have some unique properties when it comes to their conformations. And we're not going to take such a deep mathematical look like we did in the previous lecture, but we are going to take more of just a relative look at the different energy levels of cyclohexanes. So just to recap, cyclohexane looks like a hexagon, and they are very common in organic chemistry. So this is called cyclohexane. Now, at first glance, you might think of the cyclohexane as being flat, but it's not. So at first glance, it appears flat. So you might imagine it kind of looks like a pancake. Just try and draw it in a kind of flat form, just like a flat pancake. But it turns out this would not be good, because if you look at the angles inside of a hexagon, if you remember from your geometry class, the angles inside of a hexagon are 120 degrees. Now, I didn't draw in any of the hydrogens on the cyclohexane, but note that all the carbons in cyclohexane are sp3 hybridized, and so 120 degrees would not be good for sp3 hybridized. sp3 hybridized prefers 109.5 degrees, if you remember the bond angles. So 120 degrees, not good for sp3. And the angle's too big. So to ensure a perfect 109.5 degree angle, like every sp3 carbon wants, cyclohexane puckers. Okay, cyclohexane puckers. There are two ways for cyclohexane to pucker, and let's take a look at those two possibilities. So two ways, and it turns out one of the ways is better than the other. The first way is called the chair. And so it looks, and this takes some practice to draw, so try and draw this, but just keep in mind that it takes a little bit of practice. And so basically what you can see is that in the chair puckering form, 3 of the atoms of cyclohexane go down and 3 go up to create this sort of zigzag form. And obviously there's hydrogens all over on all these carbons, but I'll just draw in 2 of the hydrogens. And you can see, let me actually move my chair down a little bit here. You can see that the hydrogens are nice and they're far away from each other. They're staggered. The 2 hydrogens are staggered. So this is called the chair. And it is lower in energy. There's another way that the cyclohexane can pucker, and it is called the boat. The boat looks like this. And this is where the 2 ends of the cyclohexane kind of go up, kind of bend upward. And you can see in the boat, there's a few bad things going on. The hydrogens on the top carbons kind of bump into each other. So they call those the kind of like the flagpole hydrogens, kind of like the flag on a boat bumping into each other. And then also, the hydrogens that are down here are eclipsed with one another. So there's eclipsing hydrogens, which we know are bad. So this is called the boat, and it's higher in energy, aka bad. So what we're going to see is that cyclohexanes, they prefer the chair form. But it's not that simple. So it turns out that the chair form can undergo a rapid equilibrium called a ring flip. So let's just take a look. I'm going to redraw the chair, and I'm actually going to draw in all the hydrogens this time. Okay, there's my chair. and I'm going to draw in all the hydrogens on the chair. Each carbon on the cyclohexane is going to have a total of 2 hydrogens attached. Just kind of like this. Now I'll draw in the hydrogens. All right, wow, there's a lot of hydrogens on the cyclohexane, but notice how all the hydrogens are staggered perfectly with one another. And you'll also notice that there's 2 flavors of hydrogen in the cyclohexane. There's some hydrogens that are pointing straight up. So I'll highlight those in green. So these 3 hydrogens are pointing straight up, and also on the bottom there's 3 hydrogens pointing straight down. And those hydrogens have a special name. They're called axial, because they're like the axis going straight up or straight down. Then there's some other hydrogens which appear to be more pointing towards the side. Of course, chemists would give names to all of this. So nerdy. So these 6 hydrogens are kind of pointing to the side, and those have a different name called equatorial, because they're kind of like the equator, pointing left and right, you know, not straight up and down, but more of an angle. So these are called equatorial. It turns out that the chair can, like I mentioned, flip over. So it kind of wiggles a little bit. I'll try and show a live video of this during our live hour so you can watch a kind of animation of how it wiggles. But the left side, which is kind of pointing down, this side here kind of flips up, and the right side, which is pointing up, kind of flips down. So let's see what happens after the ring flip. And these 2 forms of cyclohexanes exist in equilibrium, so it's always oscillating between these 2 forms. So the ring flip looks like this, where it's kind of like flipped mirror image wise. And I'll draw in all the hydrogens again. I don't know, I'm going to kind of draw my ring flip again, just try to do it a little bit better. Is that better? That's pretty good. That's a pretty good ring flip. I'm not a beautiful artist. This takes a lot of practice to draw these really well. So we'll do some practice drawing these in class. I'm gonna do it one more try. One more try. Just a little bit longer, I think. Looks better. Okay, that's pretty good. Okay, now I'm gonna draw in all the hydrogens again. H. Notice how each carbon is that tetrahedral shape. Okay, there's all my hydrogens. And again, I'm going to go ahead and highlight all of my axial hydrogens in green. So we've got my 3 axials on the top and my 3 on the bottom. And then all my equatorials in yellow. 1, 2, 3, 4, 5, 6. And what's cool about when you do the ring flip is that all of the axial hydrogens on the left side become equatorial when they move onto the ring flipped right side. So actually, if we mark this carbon with pink, let's watch what happens to that pink carbon. It actually moves up here. So when you do the ring flip, that carbon kind of flips upward. Can you see that? So when you do the ring flip, all of the original axial groups become equatorial and vice versa. Now, of course, in this example, since they're all hydrogens, it's impossible to keep track of where they go. They just sort of seem to just stay in place. But if we start to add some substituents onto the cyclohexane, then we can actually watch the substituents move around when it does the ring flip. So let's go ahead and give that a try. So we'll call this part substituted cyclohexanes. All right. So let's take a look at a very simple substituted cyclohexane. Let's take a look at methyl cyclohexane. It's a cyclohexane that has 1 methyl group on it. And so let's go ahead and draw the chair form of this cyclohexane. So this is the sort of top-down view, but let's draw the side view, which is the chair. Okay, so here it is, and here is my CH3 group. It's pointing up. So you saw how I made it a wedge. That meant it was pointing up. So that's why when I draw my chair, I have the CH3 pointing up. Now let's do a ring flip and see what happens. When I do the ring flip, the left side goes up and the right side goes down. Okay, and there's our new cyclohexane after the ring flip. And now this carbon right here becomes this carbon right here, and the CH3 group needs to stay facing upward direction. So it's still pointing up, but now look what's happened. The CH3 group has switched from being in an axial position to an equatorial position. So this was axial, and now the CH3 is equatorial. So when you do a ring flip, axial groups become equatorial groups, even though they still point in the same direction. In this case, the CH3 group was still pointing up. It just went from being axial up to equatorial up. Now, it turns out that there is a stability difference between these two cyclohexanes. It turns out that groups that are equatorial are lower in energy, meaning that these two ring flip forms are not equal. This form is lower in energy because the CH3 group is equatorial. So we'll just say most stable. CH3 is equatorial. So that's really all the analysis we're going to do here, is we're going to draw chairs. We're going to figure out which chair form puts the most number of groups equatorial, and we'll just say that's the lowest energy. I'm not going to make you actually calculate the energy like we did with the previous lecture where we actually added up all the different values. You could do that same analysis here, but we're not going to bother with that. I'm going to be nice to you guys, and I'm just going to ask you, can you tell me which one is more stable and which one is least stable? Let's do another example. Okay, let's do a cyclohexane with 2 methyl groups on it. So put a methyl group here and a methyl group here. Okay, let's draw the chair for that one. So I'll start by drawing my chair. And I'll pick this carbon to be this carbon here. And so we have the methyl group pointing up at that position. So here we go. There's a methyl group. And then we skip over to 1, 2, and there's another methyl group. So we go 1, 2, and put our other methyl group right here. Okay, so that's the first chair form. Now let's do our ring flip. Okay. Remember now that this carbon, which was in pink, is now down here. Our methyl group is going to switch from being an axial methyl to an equatorial methyl, but it's still going to be facing up. There it is. Now we skip 1 carbon, 1, and then here's our other carbon, which has the methyl group on it. It's still going to be facing up, but it's going to be equatorial. And so there's the other chair form. So which one of these is more stable? The second one is more stable because it has both methyl groups equatorial, and that is more stable. So winner. Okay. Let's do another one. Let's do a cyclohexane with 2 methyl groups again, but this time we'll put the 2 methyl groups right next to each other. Okay, we'll draw our chair. Okay. We'll just arbitrarily call this carbon, but the methyl group is facing up. And then 1 carbon over, we have another methyl group, and it's also going to be facing up. So it's going to look like this. keep in mind, now one thing that I think a lot of students struggle with is they look at a carbon and they don't know where the axial position goes. Is the axial is either going to be straight up or straight down? And so what I want you to do is look at the bend of the backbone of the cyclohexane. Can you see how this is kind of an arrow pointing up? So that means the axial position is in the up position. But now look at this carbon here. See how it's an arrow pointing down? So that means the axial is in the down position. And then again, here we have an up arrow, so the axial is going to be facing up. So every carbon has an axial and an equatorial position, and it alternates up, down, up, down, up, down around the ring. So since this carbon, the axial position is up, that means the next carbon over, the equatorial position will be up and the axial position will be down. So that's what this looks like. Now let's do our ring flip. And we'll keep track of our pink carbon here. So now that axial methyl is going to become an equatorial methyl, but still facing up. And then our equatorial methyl here will become an axial methyl, but still facing up. So it'll look like this. Okay, so which one of these is more stable? They're tied because each one of them has one axial and one equatorial. In the first case, this methyl is axial and this methyl is equatorial. And in the second case, this methyl is equatorial and this methyl is axial. So it's a tie. So sometimes there isn't a clear winner and sometimes there's a perfect tie. So this is going to be tied. No clear winner. All right, let's do one more example here. Let's do methyl, and let's do a big group. Let's do a tert-butyl group going down. Okay, let's draw a chair. You'll get really good at drawing these chairs. I want you to practice with that. And then let's see what we got here. So we'll call this our pink carbon. So we've got a methyl group going up, and then we go 2 over, 1, 2, 1, 2, and then we have a tert-butyl group going down. So that's going to be in the equatorial position. All right, and now let's draw our ring flip. Okay, our CH3 group is still facing up, but now it's equatorial, and our tert-butyl group, which is 1, 2 carbons away, 1, 2 carbons away, is still facing down, but now it's axial because it was equatorial. Okay. So in the first case, we have the methyl group axial, and then the second case, we have the tert-butyl group axial. So actually, there is a clear winner here. Which one do you think is lower in energy? The first one is lower in energy because the large tert-butyl group is equatorial. So if you have to have a group that's axial, you want it to be the smallest possible group. Obviously, a CH3 group is a lot smaller than the tert-butyl group, which is 3 methyl groups in 1. So putting the large, bulky tert-butyl group axial is better. So this is the major because it avoids large group axial. Puts the large group equatorial. All right. So let's take a look at a exam-like question. So this is nice. I gave you some cyclohexanes now with 3 substituents on it, and I even drew the chairs for you so you don't have to draw those. And I even numbered that I want this carbon to be carbon number 1. Okay, so let's convert our top-down views into our chair views. So at the position 1, we have a methyl group and it's facing up. Okay. On our next carbon over, we have a methyl group and it's facing down. And then 2 carbons over for that, we have another methyl group that's facing down. Okay, so that's the first chair form. Now let's do the chair flip. All of our groups that were once axial will become equatorial. So our CH3 goes like this. Our CH3 goes like this. Actually, the angle doesn't really matter, but I think this angle looks a little bit better. CH3 looks like that. It's equatorial now. And then skip 1, and then we have another CH3 going down. Looks like that. Notice how I flipped the CH3 to say H3C. That was just so that I can show that it's still the carbon that's being attached rather than hydrogens being attached. Okay, so which one of those seems to be the most stable? The second one is the most stable because it has all three groups equatorial versus the first one, which has all three groups axial. Okay, let's do the next one here. So again, we have in position 1, we have a CH3 group going up. I see I'm kind of low on room here. Let me just make this a little bit smaller on this one. Okay, so we have a CH3 group going up. And then on the next carbon over, we have a CH3 group also going up. So that's going to be up equatorial. Then let's see. We skip 1, 2, 3. 1, 2, 3. We have a carbon that's going up. CH3. Okay, let's do our flipperoo now. This carbon here goes on to this position, and it's still facing up, but now it's equatorial. 1 carbon over, still facing up, but now it's axial. And then skip 3. 1, 2, 3. It's still facing up, but now it's equatorial. All right, so which one of these is the most stable? Well, if we look at the first one, we've got 2 groups axial. But if we look at the second one, we have 2 groups equatorial. So most groups equatorial is more stable. So again, we have our second structure as being the more stable chair. Okay, there'll be a lot of practice on this on problem set 2. So go ahead and try out problem set 2 if you'd like some more practice drawing chairs and putting in the substituents and deciding which chair flip is the most stable. In other words, which one has the most groups equatorial and the most large groups equatorial. All right, so that's all you need to know about the conformations of cyclohexanes. Let's move forward into another quick little discussion about a concept called conjugation. Conjugation comes from the Latin. Is Latin? I think Latin should be capitalized. So it comes from the Latin, con, which means with, and jugare, I don't know if that's how they would say it in Rome, which means joining. So the overall meaning of conjugation means to join together. And so for our conversation about conjugation, we'll need to recall our bonding of ethylene. Which we did in our first lecture. And if you remember our bonding of ethylene, it looked like this. And we had some p orbitals that were lined up with each other, and that created a pi bond. So ethylene was that double bond, CC double bond, and it has those p orbitals that are lining up to create a pi bond. One thing that's interesting about pi bonds, and this is different from our single bonds, is that pi bonds cannot rotate. They can't do those conformational rotations because if you rotate the pi bond, look what happens. So I'll just do this little arrow to show that we're going to rotate. So let's say we rotated it. I'm going to draw a little perspective drawing here. So the right carbon will kind of leave the same, but then the other carbon will kind of rotate 90 degrees. And now look what happened. The p orbitals are no longer lined up with each other. They're at 90 degrees from each other. So what that means is the pi bond was broken. So if you twist a CC double bond or triple bond, you're going to snap those p orbitals and cause them to break. So that's not good. So we don't really talk about conformational analysis with compounds that contain pi bonds because they don't rotate. They're locked in place. So, but what's interesting about this is that conjugation naturally follows from this. And what conjugation is that multiple pi bonds will line up and they will become locked together as one long pi bond. That's conjugation. So multiple pi bonds line up. Let's take a look at what that would look like. So let's say we had a compound where we had pi bond, single bond, pi bond. And if we draw the p orbitals on all those carbons, it would look something like this. P orbital, p orbital, p orbital, p orbital. And see how they're all lining up? These are not just isolated pi bonds anymore. There's one long overlap occurring, and we call this an extended pi system. So it's not multiple pi bonds, it's multiple p orbitals. So what that means is this is not just pi bonds that can do this, but also just the alignment of p orbitals. So p orbitals can participate as well. Let's take a look at an example. Okay, so here we have a pi bond next to a carbocation, which is a carbon with a positive charge. And so if you calculate the steric number of that carbon, you'll find that it's sp2, which means it has an empty p orbital. So if we drew the sort of orbitals, the p orbitals on this compound, we'd have two filled p orbitals that are forming the pi bond. But then we also have an empty p orbital on that carbon with the plus charge that can also line up and get some love from the conjugation effect. So this is going to be empty p orbital can get some love. It's nice for that empty p orbital to not feel so alone. It can line up with some p orbitals who are filled, and they can share some of the electron density into that empty p orbital. Another case where this comes up is something like this. Remember that if an atom can participate in resonance, it's sp2 hybridized. So that means this oxygen, which can participate in resonance, is sp2 hybridized, which means it has a p orbital on it. Anything sp2 hybridized has a p orbital left over, if you remember back from our hybridization discussion. So what will the orbitals look like on this? All kind of lining up here. And we have a conjugation system going on here as well. So this is conjugation. So what you'll notice here is that conjugation is related to resonance. Conjugation is related to resonance because it's electron delocalization. And that is stabilizing. So here is some proof that conjugation is stabilizing. And for this, we're going to take a look at our first chemical reaction in this class, first organic reaction. So let's take a look at this organic compound here. And what you'll notice is that there are two alkenes. There's two pi bonds in this molecule, but they are isolated. They are not next to each other. So we call these isolated pi bonds. And because they're isolated, they're not conjugated. Conjugated, the pi bonds have to be one after another. And the reaction we're going to do is we're going to do something called a hydrogenation reaction, where we combine the alkene with hydrogen gas, and then we're going to apply a platinum catalyst. And what's going to happen is this reaction deletes double bonds and just turns it into an alkane. And we can very carefully measure the temperature change in this reaction, and that will allow us to calculate delta H, which is the enthalpy, and we find that this reaction loses 61 kcals per mole. All right, now let's take a very similar example. It's another compound with 2 pi bonds, and this time we're going to just make those pi bonds conjugated with each other. They're going to be next to each other rather than isolated. Okay, so it really is almost the same compound here. I mean, it's got the same number of carbons, the same number of hydrogens. The only difference between the top compound and the bottom compound is the positioning of the double bonds. So what the chemists believed was that there should be no difference in energy between these two hydrogenation reactions. After all, the product is totally the same. However, when they measured the delta H of this reaction, they found it was not negative 61, but rather it was negative 54 kcals per mole. The only way that that's possible is if there's some sort of extra stabilization that's occurring in the second molecule that's not occurring in the first molecule. So what must that stabilization be? It's conjugation. We can also graph this. We can also represent this in graphical form of what's going on here. So if I draw a little axis, and we say the y-axis is energy, and on the x-axis, we'll just have like the place for all the different substances to be. So we have this first molecule here, and we'll have our second molecule at a little bit lower energy, and then at the very bottom we'll just have our product here. And so when we do the hydrogenation reaction, the first compound, the isolated diene, isolated compound with 2 alkenes, which is sometimes called a diene, loses 61 kcals per mole. Whereas the second conjugated diene loses 54 kcals. And so this difference in energy between 61 and 54 is called the stability due to conjugation, or conjugation stability. So this is proof that conjugation is a stabilizing effect. Okay, now I'm never going to ask you to do calculations like this. I'm just trying to show you the concepts. Let me show you what an actual exam style question will look like. So example of an exam style question. I could give you a molecule, let's say something like this. Let me just make it a little bit neater here. Okay, and then I'm going to say circle all the conjugated atoms. Okay, so in order for an atom to be conjugated, it needs to be part of a double bond or part of an sp2 hybridized atom that is alternated away from another double bond or sp2 hybridized atom. So for example, all of these carbons are conjugated because they're part of alternating double and single bonds. Also, when we enter the ring, all of these atoms are also conjugated because they're all part of double bonds that are next to another double bond. Now, what about this oxygen here? Is this oxygen conjugated? What is the hybridization of that oxygen? It can participate in resonance because it's a lone pair next to pi. So that means it's sp2, which means it has a p orbital. So that is also conjugated. So we would circle that oxygen as well. This carbon here, sp2 hybridized. It's also part of the conjugated system. And then finally, this oxygen up here is part of the conjugated system because it's also sp2 hybridized. If you do the hybridization calculation by calculating the steric number, you'll see that that oxygen is also sp2 hybridized. But now here, look, there's an sp3 hybridized atom, and that blocks conjugation. Because sp3 hybridized carbons, or any atom that's sp3 hybridized, does not have a p orbital, and so it cannot send that conjugation signal any further. It acts like a barrier blocking any more conjugation from happening past that point. And over here we have another alkene, but it's not conjugated to any other p orbital, so it is not itself conjugated. The conjugation to the rest of the molecule was blocked by this sp3 hybridized carbon. So I've just circled now all the conjugated atoms. Now it turns out that conjugation has some significant consequences, and I do want to discuss those consequences. However, we cannot explain these consequences using valence bond theory. We need something called molecular orbital theory. Which is an upgraded version of valence bond theory. And so molecular orbital theory is really boring and kind of complicated, but in a nutshell, this is what it is. In molecular orbital theory, it says that atomic orbitals combine to form things called molecular orbitals. So, in other words, we could have two atomic orbitals, say two p orbitals, and I'll shade them in to show the phasing. They can combine in two ways. They can either combine in phase or out of phase. Okay. So these are two p orbitals, and they can either combine in phase or out of phase, and these are atomic orbitals. And when these atomic orbitals mix, they can create two they can create two molecular orbitals, one of which is bonding and the other of which is anti-bonding. So the first combination of atomic orbitals, where they're in phase, creates a bonding molecular orbital that looks like this. The electron clouds kind of combine in a way that's constructive. So this is called the bonding MO. And we sometimes call this pi. This looks like a pi bond. Or the out of phase could combine, but they don't really want to combine. They kind of repel each other because they have destructive interference. So you can see the little lobes kind of are repelled away from each other. It looks kind of like a butterfly. And they're like, ugh, I don't want to be anywhere near you because we are not in phase. So that's the kind of picture that occurs if you try and mix these two guys together. Now, again, I'm never going to ask you to draw these pictures. I'm just showing you this so that I can show you something interesting about conjugation. You're never going to have to draw pictures like this in this class. So we call this the anti-bonding MO. And this is sometimes called pi star. The star means anti-bonding. All right. So with this information, we can actually construct a MO diagram for ethylene. Okay. So this is going to be the MO diagram for ethylene, which looks like this. the simplest alkene that you can have. Okay. We have two molecular orbitals. We have pi 1 and pi 2. We're just going to increase in energy as we go up. So pi 1, the lower energy scenario, is when we mix the two p orbitals, the two atomic orbitals, in phase. And then pi 2 is going to be the antibonding case where we mix them out of phase. Okay. And then right in the middle, we can draw a dotted line to separate these two. And everything above that line is antibonding. And everything below that line is bonding. Okay. And here are orbitals, and we can start to fill them up with the electrons. So how many pi electrons do we have in ethylene? 2. There's only one pi bond. One of these lines of the double bond is a pi bond, and each bond has 2 electrons. So ethylene has 2 pi electrons, so we'll just fill it in like this, obeying the normal electron filling, the Aufbau principle, the Pauli exclusion principle, Hund's rule. We would just put in those 2 electrons in that lower energy orbital. So it turns out that this pi 1, we can call that the HOMO. HOMO is an acronym, and it stands for highest occupied molecular orbital. And our pi 2, we can call that the LUMO. That is a name that means lowest unoccupied. Molecular orbital. And the whole reason that we're doing this is that we are interested in something particular, this difference in energy between the HOMO and the LUMO. The difference in energy between the highest occupied molecular orbital and the energy of the lowest unoccupied molecular orbital. They're close to each other. They form like a little sandwich. That energy is called delta E, and it's equal to the HOMO-LUMO gap. It's the difference in energy between the HOMO and the LUMO. And so this is going to have an interesting consequence that you'll see on the next page. Let's now try to draw a MO diagram for butadiene, which is a little bit more complicated than ethylene, but we'll see we'll do it exactly the same way. So MO diagram for butadiene. Again, I'm never going to ask you to draw these diagrams. I'm getting somewhere that's very simple. You're going to be like, why did you have to make this so complicated? I want to share with you the theory. Butadiene looks like this. It's like ethylene, but it's conjugated once. Now let's construct our diagram. So we'll have our energy. We'll just abbreviate that E. Okay, and since we have 4 atomic orbitals now, because we have 4 carbons involved with our pi system, we will have 4 molecular orbitals that we can form. So I'll just draw 4 lines, and let's arrange in order from lowest energy to highest energy the 4 orbital combinations. Okay, so the lowest energy combination is when all the p orbitals of our butadiene are in phase with each other. Okay, all in phase. Now, a little bit higher in energy, we are going to add 1 node, which is where we're going to have a phase flip in the middle of our sequence. So the next highest energy will be the 2 molecular orbitals on the 2 atomic orbitals on the left are in phase, but the 2 atomic orbitals on the right, who are also in phase, are split in the middle. So there's this little, what we call a node, splitting the 2 atomic orbitals. Okay, now we need to draw a third possibility. So now we're going to have 2 nodes. So we'll have a node here and a node here. And so what will that look like? It'll look like this. It's higher energy still. And then the highest possible energy is where we have just complete alternation, a total of 3 nodes. You notice that each time we go up in energy, we increase by 1 node. So this one here will be down, up, down, up. All right, and now we'll draw our energy lines. So we have pi 1, pi 2, pi 3, and pi 4. We can draw a line right through the middle to split the pi's up. And what we can see is that we have our anti-bonding up here and our bonding down here. And now let's fill in some electrons. How many pi electrons does butadiene have? We have 2 pi bonds in butadiene. Each pi bond contributes 2 electrons, so that's a total of 4 electrons. So 1, 2, 3, 4. All right, who's our HOMO? Our HOMO is pi 2. And who's our LUMO? Our LUMO is pi 3. And what we'll find is that if we add more double bonds to our butadiene, so if we go to hexatrine and so on and so forth and keep adding double bonds, the HOMO-LUMO gap gets smaller and smaller. That's because this whole picture starts getting more and more compressed. With every additional pi bond that we add another 2 atomic orbitals, and we add another 2 molecular orbitals. So this whole picture just keeps getting more and more and more compressed, and so the delta E gap gets smaller and smaller. So we'll just say delta E gets smaller with every additional pi bond. That's it. That's all I wanted the take-home message to be, is that with each additional pi bond, delta E gets smaller. Who cares? That would be the next question. So take-home message, let's just summarize here. Increasing conjugation that means more pi bonds, one after another, decreases the delta E. Which is the HOMO-LUMO gap. Okay, why does this matter? An old formula you may remember back from general chemistry, which is energy equals Hc over lambda. This formula is a relationship between energy and light, which is lambda, which is the wavelength of light. So it turns out that photons can interact with electrons. Let's draw a little picture to represent what could happen. Let's zoom in on the HOMO-LUMO pair of some molecule. So let's say this is our HOMO and this is our LUMO. And in our HOMO we have 2 electrons inside and the LUMO is empty. A photon comes along, so this will be our photon of light, and hits the electron in the HOMO. So this is a photon. And what can happen is an excitation where it promotes one of the HOMO electrons into the LUMO orbital. Okay. So what can happen is, for a brief moment, the 2 electrons in the HOMO get split up. 1 electron stays down there in the HOMO, but another one gets shot up to the LUMO. Why does this matter? What this means is that if a photon of a particular energy, it has to be just the right amount of energy to promote from HOMO to LUMO. With a precise energy equal to the HOMO-LUMO gap energy. So the photon needs to be equal in energy to that gap exactly for this transition to occur. So if a photon with a precise energy equal to delta E of a molecule, it may promote, so if a photon hits, I'll just say interacts with. So if a photon interacts with a precise energy, if a photon with a precise energy interacts with a molecule, I don't know why I'm having so much trouble writing this out. So if a photon with a precise energy equal to delta E of a molecule, it may promote an electron from HOMO to LUMO. And what this means is that the molecule can absorb light. And what happens if a molecule absorbs light? It can appear to have a color. And so all of this conversation was just to talk about how we can predict, in a way, the colors of organic compounds. So let's take a look at two organic compounds, one called beta-carotene, which is found in carrots, and one called lutein, which is found in egg yolks. Turns out the orange color of carrots is due to conjugation, and the yellow color of eggs is also due to conjugation. And so let's take a look at what this means. So if delta E, that is the HOMO-LUMO gap, is very large, a high energy photon usually in the UV region that means short wavelength, lambda is wavelength, can be absorbed. This situation happens when there is little to no conjugation. That's because the more conjugation you have, the smaller the delta E gap becomes. Okay. On the other hand, if delta E is very small, a relatively low energy photon such as visible light that is a long wavelength can be absorbed. And this happens when there is a large amount of conjugation. So you can see in this picture here, the carrots and the eggs, they contain molecules with a large amount of conjugation. So that means these molecules absorb visible light. And whenever something absorbs visible light, it appears to have a color. That's the take-home message here. And so let's see why carotene with its 11 conjugated bonds appears orange, but lutein with its 10 conjugated bonds appears yellow. So beta-carotene has 11 conjugated pi bonds. I've highlighted them there in the picture. And what you can see is that beta-carotene is more conjugated than lutein. So because beta-carotene is more conjugated, that means the HOMO-LUMO gap is small, very, very small. So that means it's going to be able to absorb a lower energy light. So let's take a look at this little rainbow here and see what happens. So because beta-carotene is more conjugated, it's going to absorb indigo light, which is relatively low energy light, and so it's going to be perceived as orange. But lutein has 10 conjugated pi bonds. So the HOMO-LUMO gap is a little bit bigger. So it's going to absorb higher energy light. It absorbs violet light, and so it appears yellow. You could imagine if you had a compound that had like 22 conjugated pi bonds, something like lycopene, which is found in tomatoes, that would absorb even more low energy light, and so the color might appear red. If you had something with a ton of conjugation, it would absorb very low energy light, like red light, and then it would appear green. So that's really the take-home message from all of these pictures. The more conjugation you have, the lower energy light it absorbs, and if it absorbs a certain energy of light, then the compound itself will appear a certain color. Okay. Now, be aware, if you don't have enough conjugation, then it will absorb very, very high wavelengths of light in the ultraviolet region, so we will not perceive that as having any color. A compound that absorbs ultraviolet light doesn't appear to have a color to our eyes. Similarly, if a molecule has tons and tons and tons and tons and tons of conjugation, and it has a very, very, very small HOMO-LUMO gap, it's going to absorb very, very low energy light, so low it could perhaps start to absorb infrared light. In that situation, it will also be colorless because a compound that absorbs infrared light doesn't appear to have a color to us. Only when a compound absorbs in the visible region does it appear colored. All right, so that's pretty much all you need to know about conjugation. You don't have to draw those diagrams or draw those pictures, but I may ask you to predict the color of an organic compound relative to another compound. Like I could give you two molecules, and I'd say one molecule has a conjugation of 13 and another molecule has a conjugation of 10. Which compound is more likely to appear yellow? And then you would use this chart and your knowledge of the relationship between conjugation and color to answer that question. We'll do some practice like that in our live hours. Okay? It's also going to be some practice on problem set 2. All right, that's it for now. Talk to you later.